So, I want you to imagine a world where the most complex, headache-inducing transactions in your life just happen.
Right. Automatically.
Yeah, completely automatically. Things like securing a collateralized loan, executing a multi-party escrow, or even running the treasury of a massive business.
All happening in seconds.
Exactly. Strictly governed by code. Not a single lawyer, no traditional middlemen taking a cut or slowing the whole process down. Welcome to today's deep dive. Today we're exploring the actual architectural reality of Ethereum and the Web3 development ecosystem.
It really is a profound infrastructural shift. I mean, we're
Right.
moving away from traditional siloed server architectures and looking at how distributed state machines are just fundamentally changing digital agreements.
Yeah, and to map out this ecosystem for you, we've got a pretty dense stack of sources today. We're pulling from the foundational architecture outlined in Ethereum for Dummies, alongside some really heavy-hitting developer guides from Alchemy and Consensus, plus a few foundational Web3 modules.
Good mix of theory and practice there.
Totally. And our mission for this deep dive is to cut right through the marketing noise. You likely already know the basic definition of a blockchain, so we're going to bypass the elementary stuff. We want to give you a highly comprehensive, beginner-friendly shortcut to understanding how decentralized applications are actually architected, compiled, and deployed.
And before we really jump in, just a quick note on the nature of this material. The sources we're reviewing deal heavily with decentralized finance, bypassing traditional banking, and shifting economic power.
Right, which gets political fast.
It does. These concepts frequently intersect with politically and economically charged debates from both sides of the aisle regarding monetary policy and state regulation. So we want to be entirely clear that we are not taking any sides here.
Not at all.
Right. Nor are we endorsing the specific political or economic viewpoints embedded in these Web3 materials. We're simply here to objectively report on the technical ideas and the architectural frameworks contained in the original source documents.
Okay, let's unpack this. Where does the architectural deviation from traditional blockchains actually begin? Because to really grasp the engineering behind Ethereum, we have to look at the limitations of its predecessor.
You mean Bitcoin?
Right. Bitcoin proved that a decentralized ledger could securely transfer value. But the consensus guides note that Bitcoin's scripting language is deliberately non-Turing complete.
Yeah, it was engineered to be a calculator, incredibly secure, but intentionally limited in its computational scope to prevent network attacks.
And that limitation is exactly what sparked the big shift, right?
Exactly. Back in 2013, a 19-year-old Vitalik Buterin realized that blockchain technology was functioning as a highly restricted, distributed database.
Which is great for sending money, but not much else.
Right. So Ethereum's key innovation was introducing a Turing-complete environment, which, to put it simply for you, means it can theoretically compute any arbitrary program, provided it has enough resources.
It can compute anything that is computable.
Exactly. You transition from a simple distributed ledger to a global distributed state machine.
And the engine executing those state transitions is the Ethereum Virtual Machine, or the EVM. And when developers talk about the EVM, they aren't talking about, like, a server sitting in an AWS data center.
No, not at all.
It's a single, continuous, decentralized computer running on every single participating node simultaneously. So when you deploy a smart contract, you are compiling code that runs across this massive, global runtime environment.
What's fascinating here is the deterministic nature of that execution. The sources reference this classic analogy from Nick Szabo, the vending machine analogy.
Oh, I love this one. It makes it so concrete.
It really does. Think of a vending machine. It has hard-coded physical logic. If input equals $1 and selection equals A1, release the soda.
There's no shop assistant you have to trust, no cashier's judgment.
Right, and you can't cheat the machine, and the machine can't cheat you. In the EVM, a smart contract operates with that exact same deterministic rigidity. If the network is given the exact same inputs, every single node running the EVM calculates the exact same resulting state. It is completely trustless.
Zero ambiguity. But the architecture of a Turing-complete global computer introduces a massive vulnerability. The Alchemy docs highlight this heavily.
The halting problem.
Yes. In computer science, you cannot theoretically know if a program will eventually stop running or if it's just going to run in an infinite loop. So imagine if anyone could just upload arbitrary code to the EVM.
Someone could deploy a recursive loop, max out the computational bandwidth, and just crash the entire global network.
Exactly. And that architectural threat is the entire reason the concept of gas exists. It's not just a pesky transaction fee to annoy you.
Right. It's a fundamental security mechanism. Gas bounds computation. Every single operation in the EVM, adding two numbers, storing some data, requires a specific amount of gas to execute. You literally have to pay for the computational work to prevent spam.
So that infinite loop problem is solved pretty elegantly. The EVM will execute your infinite loop, sure, but it deducts gas for every single operation.
And the moment your gas runs out,
Boom, execution halts. The transaction fails, the state reverts, and the network just moves on. The attacker just drains their own wallet for nothing.
exactly. But how we price that gas actually underwent a massive overhaul with the EIP 1559 network upgrade.
Right, the old system was kind of a mess.
It was a blind first price auction. You just guessed how much to pay a miner to process your transaction, which led to massive overpaying and crazy volatility. Today, it's algorithmic.
a two-part fee system now, right?
Yes. First is the base fee. The protocol itself sets this to target blocks being about 50% full, and crucially, this base fee is burned.
Destroyed, completely removed from the circulating supply.
Right, which means under high usage, like a major NFT mint or heavy trading Ethereum actually burns more ETH than it creates. It becomes deflationary.
And the second part?
The priority fee. Since the base fee is burned, if you want to incentivize validators to process your transaction faster, you add an optional priority fee, basically a tip.
And the actual cost you pay really scales with the complexity of your contract. The Alchemy Guide breaks this down perfectly. A simple token transfer might cost 21,000 units of gas, just pennies usually.
But if you're interacting with a heavy decentralized exchange routing, math checks, multiple updates.
Yeah, you could easily burn hundreds of thousands of gas units, up to 500,000 or more. That cost of complexity is why your choice of programming language is so important.
Which brings us to Solidity. It's Ethereum's primary programming language.
And if you're coming from traditional web development, Solidity looks pretty familiar, right? Sort of like JavaScript or C++.
It looks similar, yes, but it is statically typed, and it strictly compiles down into EVM bytecode via the Solidity compiler, which is called Sulk.
The anatomy of a contract is interesting too, like the pragma directive at the top.
Yeah, Pragma just tells the compiler which version of Solidity to use, but the real strict rules come down to data storage. Because of those gas costs we just talked about, where you store your data changes everything.
Right, the EVM splits this up. You have stack and memory.
Which are highly temporary. They erase the moment the function finishes.
They're very cheap to use.
Very cheap. But then you have storage. These are your state variables. When you write to storage, that value is permanently etched into the blockchain across the entire globe.
And that is astronomically expensive.
Extremely.
Here's where it gets really interesting. Because once you write that code and deploy it to the blockchain's permanent storage, it becomes completely immutable.
It cannot be changed, ever.
Which is a double-edged sword.
Oh, absolutely. Immutability is the defining feature of a smart contract, but it's also a developer's worst nightmare. In traditional software, if you find a bug, you just push a patch on Tuesday.
But in Web3, the logic is locked. If there's a bug, you can't just patch it.
And the security stakes are massive. The sources use the DAO hack from 2016 as the ultimate cautionary tale.
$60 million lost, right?
60 million. It was a decentralized investment fund. The developers left a tiny logical flaw, a reentrancy vulnerability. An attacker used it to drain the funds, and because the contract was immutable, the devs couldn't push a hotfix. The code executed exactly as written.
So how do developers deal with that kind of pressure today?
By not reinventing the wheel. The guides heavily push tools like the OpenZeppelin library. It's a library of battle-tested, heavily audited smart contract components. If you need a token standard, you use their code.
And they also use NASDAQ, right?
Yes, the Ethereum Natural Language Specification. It forces developers to deeply document their code, explaining exactly what every function should do. It is critical for security audits.
So practically speaking, for someone listening who wants to actually build, what does the developer toolkit look like?
It starts with setting up your environment. For beginners, the guides recommend Remix.
That's the browser-based IDE, right?
Right. It has a simulated blockchain built right in, so it's perfect for simulating transactions without installing anything. But for professional, local development, you move to frameworks like Hardhat or Truffle.
And obviously you need a wallet, like MetaMask, which acts as your gateway extension to actually interact with Web3.
Exactly. And before you ever deploy to the main Ethereum network, you use testnets.
Places like Sepolia or Goerli, or local networks like Ganache.
Yes. Testnets are identical to the main network, but they use fake ETH. It offers zero financial risk. You can deploy and test everything thoroughly before going live.
So you've got your smart contract tested and deployed, but that's just the back-end logic on the EVM. You still need a website, a front end, so users can actually interact with it.
Right, and that's where we get into the battle of the front-end libraries, connecting standard web interfaces to the blockchain.
The two heavyweights mentioned in the documentation are Web3.js and Ethers.js.
Web3.js is the veteran. It's JavaScript-based, heavily endorsed by the Ethereum Foundation liturgically, and has a massive community.
But Ethers.js seems to be taking over for modern development.
It is. It's smaller. It's faster. But the real draw is that it was built with TypeScript in mind. For complex projects, that enhanced type safety is a game changer for catching errors.
If we connect this to the bigger picture, these tools, the wallets, the IDEs, the front-end libraries, they bridge the gap between traditional websites and the blockchain, creating what we call a DApp, or decentralized application.
And at the heart of most dApps are agreed-upon token standards.
Right, because smart contracts gave rise to these standards so everything can talk to each other. We all know ERC20.
Fungible tokens. Interchangeable, like regular money.
And ERC721.
Non-fungible tokens, or NFTs. Entirely unique.
But the sources also highlight ERC1155, which is fascinating. It's a multi-token standard.
Very popular in gaming. It lets you manage both fungible currency and non-fungible items inside a single contract, which saves a massive amount of gas.
Beyond tokens, these contracts are being used to build DAOs, decentralized autonomous organizations.
This is where the concepts really get pushed to their limits.
The sources use this amazing analogy of a driverless Uber. Imagine an autonomous car that gives rides, gets paid in crypto, and then automatically drives itself to the mechanic and pays for new brakes using its own profits.
No CEO, no board of directors.
Just code governing the treasury?
It's structurally brilliant. But to scale something like a global fleet of driverless Ubers or any massive dApp, you run into Ethereum's biggest bottleneck.
Throughput. The main rat only handles about 30 transactions per second.
Which is nowhere near enough for a global computer.
So how are we scaling the future?
Layer 2 scaling solutions. You take the heavy transaction processing off the main Ethereum chain to make things 10 to 100 times faster and cheaper, while still keeping the base layer security.
And there are two main ways to do this, right? Optimistic rollups and ZK rollups.
Yes. Optimistic rollups assume all off-chain transactions are valid by default. They post them back to the main chain with a delay, usually 7 days, giving people time to mathematically prove fraud if someone lied.
And ZK rollups.
Zero-knowledge rollups. They don't assume anything. They use intense cryptography to submit mathematical proof that the transactions are valid immediately. No delay needed.
Incredible. So what does this all mean? When you step back, whether you are just curious, looking to pivot your career, or prepping for a meeting, understanding is really about understanding a fundamental shift. We are moving from trusting people to trusting code.
This raises an important question, though. A thought to leave you with that isn't totally resolved in the developer guides.
What's that?
If code is law and smart contracts are entirely immutable and trustless, how do we handle inevitable human error or unforeseen logical loopholes in the future without sacrificing the very decentralization that makes the blockchain valuable in the first place?
A massive, unresolved puzzle to chew on. Thank you so much for joining us on this deep dive into the realities of Ethereum and Web3. We hope this toolkit overview gives you a much clearer lens on the decentralized future. Until next time, keep exploring.